Hey you guys, welcome back to the channel PHYSICSSIRJEE, and here we are in AITSSELECT series, and I've brought forward to you a problem which has caught my attention because of its simplicity, at the same time being able to test the students on multiple concepts. As you could see on the thumbnail here, I've written quite a few chapters which are very interesting on their own, so it should be even more exciting for students to be able to see one problem covering all these concepts all at a time. Okay, so it's a nice revision. It's a simple problem how an IIT JEE advanced examination can actually create a multi-conceptual simple situation. Let's try to go through. Okay, so I've already shared this question in the community post. I've got some right answers also for the students. So all those students would be waiting obviously for the end of the video, wherein I'll present the practice problems on a similar ideas. Okay, so please do wait till the end of the video so that you can access those particular uh, homework problems. Okay, so here I go with the formal wording. In case you have missed this community post, try to go through this particular question on your own right now. Give it 5 minutes and to come back for the problem and the concept explanation. Okay, so here we go. A very long non-conducting cylindrical shell of length L equal to 10 meter is free to rotate about its fixed axis, and light inextensible thread is wrapped over the non-conducting cylindrical surface, and one end P is being pulled with a constant force such that it has an acceleration of F divided by 2m, where m is supposed to be the mass of the cylinder. Okay, F is the force applied at point P and m is the mass of the cylinder. Then charge on the cylinder, which is supposedly uniformly distributed on its surface, okay, is 5 into 10 power k. If mass and length are given, you're supposed to calculate the appropriate value of this power k. Okay, so some information was missing in this particular question, or the clarity I should say, in an exam situation when it appeared in the AITS exam. You are supposed to assume that this q is uniform and also on the surface of the cylinder. Okay, right? And also you're supposed to take this particular cylindrical shell as the hollow one. Okay, let's move ahead step by step, concept by concept. What are the things that are going to be required to ace this problem? So first and foremost, a lot of things on the board. I keep saying, just make sure that you look at the place where I'm pointing so that I can take the lead and help you understand the things clearly. Okay, so first you should realize that the charge which is rotating about this axis contributes towards an average current. Okay, now since the charge is completely there on the curved surface, I'll divide it into strips along the length. Let's say I have each strip of length dl, it will have a charge of dq. Okay, and this dq, since it is rotating with a omega or a time period 2 pi by omega, an average current contribution would be dq divided by time period, which is quite obvious. And since this dq is uniformly distributed, I can also write that dq as q divided by total surface area multiplied by the area of this only strip, which is 2 pi r dl. Right? If you manipulate all those 2 pi's that are existing, then you would see that the value of di by dl, this and this blue colored thing, rearranges to give this value of q omega by 2 pi l. If you have the practice or the guts, actually the first follows the second, then you should be able to write this step directly. Okay, this I have illustrated for students who are seeing this topic for the first time, but good aspirants with enough practice, they should be able to write that this q omega by 2 pi is the value of this entire current and L is the total value of the length. You could have written this directly. Now, what will this current density factor going to give you? This current is now like a solenoidal current, an ideal solenoidal current, which produces a uniform magnetic field in a long cylindrical space inside. Okay, so this axial magnetic field, which is nothing but magnetic field along the axis, can be calculated using Ampere's law. Okay, now this Ampere's law that we are looking at here, right, at Amperian loop that I have considered, there is a k vector that I have already calculated. So outside the field is assumed to be 0 for a very long one. It's a decent enough assumption in this particular problem. So the Amperian circulation will be only available here, magnetic field circulation. So B into L. For this part, it is 0 because it's perpendicular, and here outside B is 0. So B into L should be equal to mu naught into current enclosed. The value of the current enclosed is this K cutting the length capital L. So once the capital L gets cancelled, you get the magnetic field produced inside as mu naught K, and I substituted the value of K here. So this is the expression I'll borrow in the to the next page. If you carefully observe here, the value of the magnetic field is coming out to be proportional to omega. Whereas in the original question, if you realize, the angular velocity was changing with time because it was having a constant angular acceleration. So we expect the magnetic field in this problem to be having a time varying effect. And whenever there is a time varying magnetic field in a cylindrical space, you expect non-conservative induced electric field to be produced, and that forms the step 2 of the problem. I hope you're excited to move ahead. So for those who are regular visitors to this channel, I've already produced a video on the induced electric field, and all the nitty-gritties, loopholes or misconceptions, all of them were covered in this, I would call it a beautiful video of 4 situations and 14 problems. So in case you're new, I have not watched this video, I would request you to watch this completely. Link is in the description or in the I button. And also the old students who have missed this concept, there is one more reason why you should watch this, because I'll be coming up with a follow-up practice problems for this particular video. At that time I promised, but I couldn't. Now is the time. I'll be definitely doing this within coming week. Okay, so for 2 reasons, just make sure you go through this one. Okay, so assuming that you have done that, right, I'm taking a page out of that particular video. This was one of the pages in that video at the start, where I calculated the E star. E star is the symbol I use for induced electric field. Okay, right? So assuming this blue colored structure, can you see on the right side? Carefully observe that blue colored structure is that cylindrical region in which magnetic field is varying with time. Okay, and because of this particular varying magnetic field, there is an E star that would be developed. Okay, right. The direction of E star here may not be correct. It all depends on whether B is increasing or decreasing. So you can make up your mind about that, but it will be tangential E stars. The E star calculation, the red colored one, is for the field inside. And whereas even though magnetic field doesn't exist outside, you would expect an E star to be present even outside. All the explanation was given in that particular video. So then I calculated the value of E star red color, that is inside points and also outside points. Whereas in this particular problem, since the charge exists only on the surface, I would require the value of E star on the surface. You could use any of these formulae because it will be a continuous function, and the value of the E star at the surface of the cylinder, which is rotating in this problem, would be capital R by 2 dB by dt, or B dot. Okay, so if I take that into account, and now we're back to the problem. So you could see again a lot of things on the board. Just follow my lead. The left side is the mechanical cause, right? You have that cylinder fixed axis. You're pulling the rope or a thread or a sheet of paper out of it, and he has already given the acceleration of a point here. Red colored point is f divided by 2m. Okay, right? And also, since this paper is going to get pulled without slipping, the value of alpha and a of this point should obey a is equal to r alpha. So I'm substituting the value of r alpha here, and say the value of f that I'm used is 2m r alpha. So keep this in mind. Because of this mechanical motion, can we say from the previous slide, the value of magnetic field was produced because there is an alpha, and therefore as the omega changes, the value of the current that would be created in this would produce an axial magnetic field. So from this previous slide, I'll borrow that. Okay, so for your convenience, I'll write the expression here. Okay, so this is the value of the magnetic field that we derived 2 slides back. Okay, so let me show that to you. Yeah, this one, this bottom rightmost thing. Okay, I've borrowed that, I've pasted it here. Now this B was supposedly function of omega. Rest of things are all constant. Since omega is going to be alpha times t, it will be an increasing function. Because of that, there will be a time varying magnetic field, and that causes an effect. Okay, and that effect, based on Lenz's law, you should all be able to visualize that it will be an opposing effect. Okay, if you are really feeling that you're pulling this one, this cylinder will resist that pull via a torque. That torque is created by E star. So I'm substituting the formula from the previous slide, R by 2 dB by dt. B dot here would be simply mu naught Q omega dot. Omega dot is alpha by definition, and that's what I have substituted here. Okay, with R by 2 multiplied. So the value of E star, which is tangential everywhere, right, changes direction, but magnitude would be throughout uniform, trying to create a torque. So if I use tau equal to I alpha equation for this, there are two torques that are there. The mechanical agent who has applied force F applies a force or a torque F into R, and there is an opposing Lenz law torque that is created, which is, because this is all uniform charge, an integration of all these dq's will produce qe's, and into R. At R distance, all the charge is there. So it's an easy torque calculation, is equal to mr square into alpha. And basically, I'm substituting for F here, the red colored thing. Can you see that here? And for the E star, I substitute this one. And you carefully observe, everywhere the alpha will become common. Okay, right? You could cancel the R square value and alpha value throughout. And then you send this term to one side and rearrange. You get Q square is something. Therefore, Q would be a square root of some of the given values in the question. When that's the reason why the person has never mentioned the value of F or alpha in the question. Okay, it's just going to be a function of mass m of the cylinder and length L. Okay, so mu naught by 4 pi substitute as 10 power minus 7 SI units, and m and L from the given information of the question, you end up getting 5 into 10 power 4 coulomb, quite a large amount of charge for this particular question. Okay, so answer for this K will come out to be 4. Okay, right. I hope you understood the concept, and you'll understand it better once you watch this particular video. And let me go ahead with the practice problems, one or two I have promised. Okay, so this is the one. A lot of students obviously pointed out in the community post about the Pathfinder question. I'm glad that they're doing some important Pathfinder questions also for their JEE advanced preparation, and this is one of them. Okay, right. And the second one, which is interesting, is also for a cylindrical region magnetic field question. Try to read the question on your own. The language is very clear. The voltmeter that you have connected here, especially if you have watched the previous video of the voltmeter, this one, you would be able to ace that particular question, the voltmeter readings and non-conservative electric fields. Okay, so the voltmeter only difference here is it is large but a finite resistance. Okay, so it is not an ideal voltmeter that is connected, but it is very close to ideal. So in that scenario, three readings are being given, E, V, and R. You're supposed to write the correct option for the inequality between E, V, and R. Okay, so comment your answer for this with the timestamp of this particular video below, and I'll respond to it. And also I'll bring up the solution of this one once you're done with watching those videos in PHYSICSSIRJEE quickies section. Okay, so yeah, the usual appeal I do at the end of every video, please do check out the description and go through the important series that are running through the channel. I've already arranged all the important videos in a nice little playlist in the main page of the channel for helping out JEE advanced aspirants whose exams coming up in few months. Okay, so try to explore that playlist also. And in case you have liked it, please do share the content with others, and also give a like to the particular video. And liked videos, YouTube algorithm pushes to more audience and thereby helping the channel. And in case you haven't subscribed, please do it. And if you have, ask your friends to do that so that we can grow our family of physics lovers. Okay, so thanks for staying this long, and see you in the next video.